All right. So let me go ahead and go to the board, and we're going to go ahead and talk about quiz number 1, just so you can see how to approach it differently, or maybe you can see where your issues were. So first of all, number 1, we had the 2 balls that were coming towards each other. One that was moving to the left, the other was moving to the right. So here is basically that picture. We have these things moving. We had some masses. I'm going to call this ball number 1 and this number 2. We had the mass of number 1 was 0.15 kilograms. And the mass of number 2 was 0.3 kilograms. So twice as massive. And then we also had velocities. Initially, this was coming in, so I'll call this V1 initial, was coming in at 0.8 meters per second. And V2 initial was actually negative 2.2 meters per second. And so this is the first thing I want to mention, because this happened to a couple of people. You have to make sure that these velocities are opposites. They are vectors, so they're moving in different directions. So when we go to actually calculate momentums and find a total momentum, we have to have these counteract each other a bit. Okay, so I'm going to make it so that to the right is positive and to the left is negative. Obviously, you can do it the other way around if you'd like, but this is how I'm going to set it up. Okay, so from this, we can find out initially how much momentum we have as a group and what our kinetic energy is as well. All right, so this is going to be pre-collision. Momentum number 1, that's going to be 0.15 kilograms times 0.8 meters per second, which ended up being 0.12 kilogram meter per second. And then momentum for the second ball is going to be 0.3 times negative 2.2, which is negative 0.66 kilogram meters per second. So what I know then is a total momentum is the sum of these, which is negative 0.54. So you can see why that difference in sign, plus and minus, is important, because now we have a negative 0.54, as opposed to if we added them directly, we would have had 0.78, which gives us way more momentum than we actually have. All right, so there's our total momentum before the collision, which we know is going to have to be the total momentum post-collision. So we'll use that to get an equation in a second. But then we're also told that this is an elastic collision, which means our kinetic energy is conserved. So let's get our kinetic energy. So kinetic energy of the first one is going to be 1/2 times 0.15 times 0.8 squared. And then the kinetic energy of the second one, similarly, we just put in its velocities and mass. And so we add those together, we get that the total kinetic energy for the system is 0.774 joules. So prior to the collision, this is what we know. So now let's go to post-collision, and let's use these two numbers to set up an equation with momentum and an equation with energy, and then we'll have a system that we can solve. So before I move on, good so far?
Yeah.
Yep, good. Thanks, Max. All right, getting some thumbs up, cool. All right, so now let's go to post. So after the collision, we're going to have 0.15 V1 final plus 0.3 V2 final is going to equal negative 0.54. So this is our momentum. The momentum of the first one plus the momentum of the second still needs to add up to the total that we had. So whatever V1 and V2 finals are, they have to satisfy this equation. We also have a kinetic energy setup. So if we take 1/2 mv squared for each of these, we're going to get 0.075 V1 final squared plus 0.15 V2 final squared, and that's going to have to equal 0.774. So these numbers are just half the masses. That's the 1/2 m part of those formulas. So that first equation is conservation of momentum, and the second one is conservation of energy. So I want to mention this at this point because, again, this affected some of you. When you go to the energy, you want to do the entire energy, not just the energy in 1 and the energy in 2 having to be the same, because we don't know that. There can be a transfer of energy in an elastic collision. So like ball number 1 may give some energy to number 2 or vice versa. So we need to do it as a total. Okay, so here's our system. So now what we need to do is basically solve the first equation for one of them, plug it into the second. I went ahead and solved the first one for V1 and put it in here. And so what that formula ends up looking like, you get 0.075 times -2 V2 final minus 3.6 squared plus 0.15 V2 final squared equals 0.774. So if I square that, distribute, group like terms, and solve, it is a quadratic. So I actually do get 2 different options. And the 2 different options here for V2 final, I get negative 0.2 meter per second, or the other one that I can get is minus 2.2. So you should have gotten 2 different possible velocities from your equation. One thing that happened to way too many of you was when you squared, you just squared the first term and the second term. Don't do that. Remember, you have to FOIL those things out. All right, so we actually have 2 different possibilities, but at this point we need to think about which of these makes sense, the real situation. So first of all, both of them are negative. And since they're negative, it means that ball 2 is going to continue moving to the left. All right, well, that's okay. And in fact, we saw in lab that that happens, right? That would have been the one when we send the heavy, don't know if you remember with the carts, when Matthew sent the heavy one in faster towards the one going the other direction. And then they ended up both moving in the same direction as the heavy one had been. So that's what's going to happen here. But one of these doesn't make sense. Which one doesn't actually make sense as a, this is what would happen?
Negative 2.0, I mean 0.2.
Why do you think the negative 0.2 is a problem, Max?
Because if it's like conserved in the momentum and stuff, they would just switch velocities. And negative 0.2 isn't one of those.
Okay, but remember that these are not the same mass.
Oh, yeah.
Since they're not the same mass, weird things can happen. Okay, so Victor, you said the negative 0.2 makes sense because the mass of the second is bigger. So it makes sense that it would continue. And yeah, they're both going to actually continue in the same direction because they're negative. But you're right. It does make sense that number 2 should be continuing this way. Well, here's the problem with minus 2.2. What was its velocity at the start?
Minus 2.2.
Minus 2.2. Does it make sense that its final velocity should be the same?
No.
No.
No, right? It should be slowed down because it just got slammed in, right? Like here they are. This one came in and bam. So even though they're coming together, this one came in and hit. It should definitely slow this guy down. So we're going to eliminate this V2 final because it just doesn't make sense in terms of the real world. Similarly, if let's say this had been like minus 3, then that would have told us that this ball actually sped up, which again is a nonsense answer. So we're going to have to kind of balance the math with the reality of the physics of the world. Because in math world, you can have all kinds of crazy stuff happen that is totally fine in terms of the equations. But in the physical world, we know we're restricted. And in this case, we're going to throw that one away. All right, well, that gave us our V2 final. So then you can just take that and plug it in, say, to that first equation to get your V1, and end up with V1 final is minus 3.2. So think about what that means. It's negative. So it's moving the opposite direction, which again makes sense. This lighter ball is going to bounce off the bigger ball and come back. And it also got sped up. So you can kind of think of it as, not think of it kind of, but think of it as the energy in 2, a lot of that energy transferred. It slowed down, so we lost a lot of kinetic energy, but that kinetic energy got put into 1 because it was an elastic collision. So number 1 has to go racing off at a greater velocity. All right, so is that okay for number 1? Questions on that? All right, hearing none, we'll move on. So question number 2, this was the golf ball that was getting struck by the golf club. And what we're told is that it goes from, or it gets sped up to 25 meters per second. And we want to figure out what average force is applied over the 2 milliseconds in which the golf club actually makes contact with the ball. So for this one, we're going to use the fact that the change in momentum is equal to force over time. And this is an average force, otherwise we'd have to integrate. But basically what we know is that the force, this is not, it's the other way around. Force times time. So force is the change in momentum over time. So that ball, again, its mass was 0.045 kilogram. We know that it started at rest. So V initial is 0 meters per second. It gets sped up to 25. So V final is going to be 25, which tells me that the change in momentum then is going to be the new momentum. So the 0.045 times 25 minus the original, which was 0 because it was stationary. And so then if we want to calculate the force, we just have to divide this by the time. So we'll take our 0.045 times 25, and then it was 2 milliseconds. So we're going to divide by 0.02, which ends up giving us 562.5 newtons. So on average, the amount of force that's being applied is 562.5 newtons. So it may start out stronger or weaker, and it may adjust, but on average, over that entire 2 milliseconds, we're supplying about 562.5 newtons. That's a lot of force. And I think these numbers are actually probably pretty reasonable in terms of mass of a golf ball and speeds that we can get. So it takes a lot of force to get these things going. All right, so questions on number 2?
This isn't a question on number 2, but have you ever taken an aluminum baseball bat to a golf ball?
Yes.
It's awesome.
You can make those things really, really fly when you if you take a aluminum bat. And one of the big reasons is because you can get that aluminum bat to such a higher speed. And then if you compare it to like what happens when you hit a baseball, because that golf ball is so much lighter, you can actually really get it cranking. You can change the momentum a lot more, right? Because even if you've got a similar amount of force, but that smaller mass, that decrease in momentum means you can actually get its energy up a lot faster. So anyway, but yep, I'm with you, Bradley. It's a lot of fun to beat things with a bat. So.
All right, so let's look at number 3. So number 3, we had the train cars that were all together, and they kept picking up more cars. So we started with 3, and they are all identical. So they all have the same mass. They're all moving at the same velocity. And we know that after they hit another car and another car and another car and a whole bunch of other cars, eventually the velocity has been decreased to 1/5 of what the original was. And so we want to know how many total cars are there. Okay, so here's how I did this. I went at the start, my mass was 3m. I'm just going to say that each of the cars has a mass of m, and we've got a velocity of v. So that means that my momentum is 3mv. At the end, we've added some cars. I don't know how many, so I'm just going to say that it's x of them. So I've got x cars, which means my mass is now x times m, and my velocity is 1/5 of what it started as, so 1/5 v. So that means that its momentum is xm times 1/5 v. But what I do know is that momentum is conserved, so that whatever I started with has to equal what I ended with. Well, the m and the v cancel. You multiply by 5, and it turns out that we need 15 cars. So if there are 15 total cars, our velocity will now be 1/5 what it started. So got to pick up 12 more. All right, so how is that for number 3? Okay,
Yep.
pretty quick and painless. All right, so let's look at number 4, the last one. And so the last one, we know that we've got 2 balls, 2 masses. We know where they are, and we also know where the center of mass is. And what we want to do is we want to figure out the location, or not the location, the mass and the velocity of the one unknown ball. So on our grid, okay, we've got one mass that's out here at 8. We know that its velocity is 0, and we know that its mass is 0.1 kilograms. We've got another mass that's at the origin. That's what we're trying to find out, everything about it. But we know that the center of mass is actually right here And we know that the center of mass actually has a velocity of 5. And I forget, was it meters per second, centimeters per second? I don't remember what the units were. We'll call them meters. So that's got a velocity of 5 meters per second. Okay, so our goal is to figure out the mass and velocity of this object. So let's start with the mass. So in order to find the mass, what we need to do is add up mass times distance, m times r, and we want to add that up for all of the different pieces. And that needs to bring us to this center of mass. Okay, so there are two approaches to this. One is kind of using the definition and using the distances from the origin. So like if we were to look at this first guy, its mass is unknown. The distance it is from the origin is 0. So right, m times 0. The other one, its mass is 0.1. And its distance away is 8. And what that's going to have to equal is the total mass, so m plus 0.1 times 2. So this gives us 0.8 equals 2m plus 0.2. Subtract the 0.2, we get 0.6, and then dividing by 2, we get 0.3. So what we know is that this unknown actually has a mass of 0.3 kilograms. The fact that it's heavier than the other one should make total sense, because the center of mass always drifts towards the heavier of the two objects if we just are looking at center mass of two objects. All right, so this is one way of doing it. And this is what I think most of you did. But I don't like to think about it this way. It's too much. It's too hard. Instead, I look at distances away from the center of mass. Because the way that I set this up, with the origin being here, is completely arbitrary. I mean, I did it because that's how they told me things were. But I'm in control of my coordinate system. So what if I were to move it so that my coordinate system was here? Well, then the most complicated part disappears. That guy is just 0. So Victor, you say, can you use X bar? Yeah, that's what this is. It really is the same. But now if we think about this, I can do the same thing that I did before, which is take the distance away times its mass. So think about this one. What it would look like is now I've got my mass times -2, because it's 2 behind. And then I'm going to add to that 0.1 times 6, because now it's only 6 units away. And that's going to equal 0. I think of that as my center of mass. And if you just move this around a little bit, you get 2m equals 0.6, which of course is going to get you to the same answer. But here's what I do. Here's how I think about it to get to this quickly. 2m. M is the mass of this thing. 2 is how far away it is. 0.6. That's its mass times how far away it is. And you can just set those things equal. So I just think this is a lot faster and a lot easier to do. So this is the approach that I like. But either way, we find out that the mass of that thing is 0.3 kilograms. Okay, so now let's go to momentum. So we want to figure out what the total, we need to get the total momentum, because we know the momentum of these two added together has to equal the momentum of the center of mass. So we're going to have 0.3 kilograms times its velocity. I don't know what that is, so we'll just call it V. We add to that the momentum of the second one, so 0.1 kilograms times 0, because it's stationary. And that's going to have to equal the momentum of the system, which is going to be the total mass, 0.4, times the 5 meters per second that the center of mass is moving. And this was the biggest issue here. People forgot to add the masses together. You got to put those guys together because it's the total mass of the system. So we get 0.3 V plus 0 equals 2. So this ends up giving you 6.6 with a bar over it. So 6.67, 6.7. I'm not a big sig figs guy, so don't worry about that. But what I know is that that particle, this one over here that weighs 0.3 kilograms, is moving at 6.6 meters per second. And notice that it's positive, so it's actually moving in the same direction as the center of mass. All right, so there's number 4. So any questions on that one?
All good.
We're all good? Okay, so again, hopefully my comments on your work.
So the comments that I put in there with the that were put in with your grades, hopefully those make sense. How I broke it down, and this is how I'm going to try to break it down always, at least on quizzes and exams. I'll basically tell you question 1, 2, 3, 4. I'll give you your score. And then if it's not complete, like if you don't get full points, I'll try to explain where you went wrong, at least best as I can. It's just a little bit harder not being able to write on them to tell you. Anyway. All right, so how about homework? Any questions on the homework? How's that going? I know Ralph asked to extend, was it chapter 11, I think, to Friday. So you guys have a couple more days. Any questions on that? How's that going?
I have a couple of questions, but I might be able to figure it out. I think I'll just wait until next class or something.
Okay, so you can ask me on Friday if there's still issues.
Yeah.
That's fine with me. Any other questions?
Can we go over question 38 and 39?
You bet. Let me go ahead and write myself a note here. So numbers 38 and 39, and those are both from chapter 11?
Yes.
Okay. Any others for me to add to my list? All right. So number 75 on chapter 10, and then Eduardo, you said the last one, was that chapter 11 as well, or is that chapter 10? Chapter 11, okay. So I've got on my list chapter 11, 38, 39, and 85. And then from chapter 10, number 75. All right, so let me share my screen. I'll pull up the physics book. And then we'll go find these guys. All right. Oh, look at that. We're on chapter 10. So I'm going to do chapter 10 question first. So let's look at number 75. So 75 spills over the page here. So let me bring it down. So it says, what hanging mass must be placed on a cord to keep the pulley from rotating? See the following figure. So the mass on the frictionless plane is 5 kilograms. The inner radius of the pulley is 20 centimeters. And the outer radius is 30 centimeters. All right, so basically we just need to figure out what mass do we put on there makes it so that everything balances out. So I'm going to go ahead and draw the picture here on the whiteboard, and then as soon as I get it drawn, I'll go back to the whiteboard view for you guys. I just want to make sure I get all the information. And again, let's see, the radii, 20 centimeters and 30 centimeters. Okay, so let me stop sharing here.
So here's our picture. I kind of zoomed in on the pulley just so that we can kind of see it a little bit better. But we've got the mass hanging from the pulley, and what we want is for this thing to be stationary. All right, so what are your ideas? How can we go about trying to set this thing up? What do we have to worry about?
Mass of the hanging block.
Okay, what is that going to do? How's the mass of
gonna-
that hanging block affect stuff?
It's either going to pull it down or pull it up.
Okay, so adjusting that, like if that mass is heavy enough, it's going to go down and pull that 5 kilogram block up the slope. If it's not heavy enough, that 5 kilogram block will pull, slide down, and cause M to go up, right? But again, we're trying to get that sweet spot where we get no motion. So Victor, you just put, you're thinking about the sum of the torques should be 0. I definitely like that idea. Because think about it, if you think about the pulley, so in terms of the masses, like if we were to draw force diagrams, in fact, let's do this. Let's actually draw the diagrams for all the different things. So for the 5 kilogram block that's on the slope, okay, so we got this one. What forces are acting on it?
Gravity.
Okay, we got gravity pulling it down. What else? Okay, a normal force, Victor throws in, good. There's definitely a normal force. And then there's also a tension. The string that's pulling on. Okay, so we've got normal force, we've got gravity, and we've got tension. And what we know is that our goal is for those 3 things to all balance each other out. All right, so that's that block. Let's go to the hanging block. So that hanging block, what are the forces acting on it? All right, so Victor just put on the chat, gravity and tension. Gravity's pulling it down, and there's the tension on the string that's holding it up. And again, we want those things to be equal. All right, so then let's go to the pulley. So what forces are acting on the pulley?
Tension.
All right, so tension, turns out there's actually 2 tensions. There's the tension that's going down to the block, and there's also the tension that's going down to the block that's on the slope. So I'm actually going to label those separately, that there's T1 and T2, which means in our force diagrams for the blocks, I need to change those as well, so that we've got a T1 and a T2, because they may not be equal to each other. And this is what's different now than what you guys did in first quarter. I imagine you probably ran into something like this where you had balancing of forces and you set those two torques equal to each other. Did you see something like that once before?
Yeah.
Yeah. But in those problems, what it would have told you is something like, assume that the pulley is massless. Kind of remember that? If not, that was always the case. You always went with, okay, so it's a massless pulley and we don't have to deal with it. But now we're allowing it to actually have mass. We want it to be real world. And so we are definitely going to get some rotation. Or at least there's the potential for rotation, but our goal is to get no rotation. All right, so there are the pictures for each of these. So far so good?
Yeah.
Yeah, we're all right. Okay, so now we get to figure out how we set this up. So let's just go and start creating the equations for all these different things. So I'm going to start with the hanging block because that's the easiest one. I know that T2 is going to have to equal the gravitational force on block M. So it's going to be whatever its mass is times acceleration, which is G. So from the hanging block, I know that T2 is going to equal M times G. So if I can figure out T2, then I'll just divide it by G and I'll get my mass. All right, well now let's go and look at the wheel, the pulley. So this one, if I have no rotation, what has to be true here?
There's a balance, so like the force is equal 0, like the sum.
Okay, except I don't want forces equaling 0.
The torques.
I need the torques equaling 0. Right? Because torque is all about rotation, and if I don't have any rotation, the forces need to balance out. Or sorry, the torques need to balance out. But we might want to think that there are a few more forces here. Because what other forces act on that wheel? So gravity. What else? Normal. You know what I love? I don't know if you guys pay attention to the chat, but Victor's always in the chat. And anytime I ask about forces, immediately he types gravity and normal, like boom, boom. So, but yes, because that's pretty much always there too. Okay, well, there's a gravity force, but that gravity force is going to be going through the center of mass, which is going to be going through the axis of rotation. And in that case, we can ignore it, right? It has nothing to do with it. And then usually the normal force is also going through there because you think about how pulleys are designed. There's usually like the little metal piece that then attaches to that center. So we're going to go with that the normal force is in here somewhere. Looks like that. But it's not going to add to the torque either. So if we want to balance the torques, then what we need to look at are the size of the forces and how far away from the central point, the axis of rotation, are they occurring. Well, it looks to me like and this is where I'm a little confused by their question, because they're giving us a interior radius and an exterior radius, but it appears that the two forces are both applying at the same spot. So I'm going to assume that we're at that bigger radius. Only way we'd need to worry about that smaller radius is if we're going to actually calculate a moment of inertia, because the moment of inertia of a ring is different than a disk. But let's just set up this torque argument. So we need to multiply by the radius. We'll call that guy R. So in terms of the torque, we're going to get R times T2. That's pulling it down, trying to make it turn clockwise. That's going to have to equal R times T1, because T1 is also the same distance away from the axis of rotation. They're both coming in perpendicular. That's why we don't have to worry about the sine stuff. And then this one is trying to rotate it in the other direction. So it balances out. So I'm thinking that probably what they meant in this question is that one of these goes to the inner radius and one goes to the outer, maybe. Because the way that they've got it worded, I don't see that it actually matters.
I'm trying to think. The way I had solved it was torque equals RF sine theta. And then I got torque is 4.9 Newton meters. And then I had used the 0.2 meters and the 5 kilograms of the one we have with gravity and with the force. So gravity times the mass, and then sine of 30. And then I set it into 4.9 Newton meters over gravity times 0.3 meters. And then I got the answer 1.7 kilograms.
When you say you got the answer, as in
Yeah.
what they had in the back of the book?
Yeah.
Okay, can you walk me through that again? I'm not a very, I don't
Okay,
catch
so-
stuff listening very well. So can you go through that again for me?
Yeah, I started with the equation torque equals radius times force sine theta.
Okay, so you're doing the good old definition of torque. Okay.
And I broke up the force is force 1 into the radius of mass 1. So I did mass 1 is the 5 kilograms.
Okay, so we're talking about the one on the slope.
Yep. And so it was 0.2 meters as to where it was like the radius, I guess, or for where it attaches to the. Oh, I see what yeah. I think it's not into the circle, it's to how far it is attached to the circle itself. That doesn't make sense. I'm trying to think of, sorry. Anyways.
That's okay.
So then I broke up force into mass times gravity.
For the block that was hanging?
This is just for the initial torque of 1.
Okay.
I wish
Well,
I could just show you.
I'll tell you what, let's hold off for a second, Ian.
Here, I'll just
Let me keep going, because I think I'm going to end up getting similar to what you had.
Yeah.
So
I'll type it.
do this. Let's go look at this block now, the one that's sliding down. And what we need is to really figure out how strong this tension is. And that tension, that's going to come from the component of gravity that's pointing down the slope, right? So you remember doing this. And basically, I need to figure out what this component is. And that's where we're going to use our trig. Because we had that this was 30 degrees, which then means this angle right here is 30 degrees. And so if I want to figure out this this portion, that was a combination of component and portion, became composition. This portion, or this component, we're going to use sine. So I know that the sine of 30 degrees is equal to that component, which is going to be T1 over the gravity. So that's going to be its 5 times 9.8. So in this, I get that T1 is going to equal 5 times 9.8 times the sine of 30 degrees, which is 49 times the sine of 30. And the sine of 30 is a half. So in order for this block to be stationary, the one on the slope, the tension that has to be applied is 24.5 newtons. And then the way I'm interpreting this question, that suggests that the second tension also has to be 24.5, because they're both applying torques out on the outside of these circles. And they're always going to be perpendicular to the radius. Like if you look at a pulley, it doesn't matter where that string is, it's always going to be tangent to the circle. So the 90-degree angle is always there in the torque formula. So it's just your R times your tension. So again, the way I interpret this, T1 would be 24.5 newtons, which then makes T2 be 24.5 newtons, which then makes M be this divided by 9.8. And I'm quite certain that that's not the number that you said, Ian. So let's see. So Ian, you got 0.2 meters times 5 times 9.8 times the sine of 30 is 4.9 Newton meters. Yep, that's definitely the torque that I would get if I were to take this T times the 0.2 meters.
Yeah.
And then you divide it by the 9.8, which would give you the mass. But you also have that 0.3. So this is where I'm saying I think they wrote the question a little bit wrong.
So maybe it doesn't actually, that second radius doesn't actually matter.
Correct.
Okay.
But like what you've got typed in there with that 0.3, it would matter if these two radii were different. If the one was out at 0.3 meters and the other one was at 0.2 meters,
yeah,
then this equation where I have RT2 equals RT1 wouldn't be true. It would be like 0.3 T2 equals 0.2 T1. What I want to do, I'm going to go back and look at the picture. And I'll go ahead and share the screen with you guys so you can look at it too. Because I wonder if it actually shows them going at different places. And it kind of does. Let me see if I can, let me zoom in here. Is that a searcher? No. So if you look at this picture, it kind of looks like the rope that's coming from the slant is coming in to basically be tangent to the black circle. And then this one that's going out, you look at it, looks like it's tangent to the gray circle. So I think their picture is suggesting that they're actually going to the inner radius for the one sloped, Jesus. Inner radius for the one that's sloped, and the outer radius for the one that's hanging. So I think that's their intention. I don't think the drawing makes it really clear unless you zoom in really closely. And for sure, the words don't make it very clear. But let's look at what happens to the equations if we do that. And then you'll see why it ends up giving what Ian found. So let me go back to this where we had the RT2 equals RT1. Now, those radii, the outer radius is 0.3, and the inner radius was 0.2. So let's just follow what happens with the numbers. So we have T1 was 24.5 newtons. So we're going to get 0.3 times T2 is going to be equal to 0.2 times 24.5. So 0.3 T2 is equal to 4.9. So then I'll divide by 0.3. And so that's equal to 49 thirds. I'm just going to leave it like that for a second. So now let's go to what we knew about the hanging mass. We knew that T2 was equal to M times G. So M is going to equal T2 divided by G. So that's going to be 49 thirds divided by 9.8. And I think that should give us the 1.7. Yeah, 1.666666. But notice that when we did it as the radii were the same, it turned out that tangent or tension 1 had to equal tension 2. But as soon as we go to a different location, those tensions are not going to be the same because their torques are not the same. Anyway. So did I thoroughly confuse everybody with number 75?
I get what you're.
Pretty much.
I get it.
So the approach, though, notice what I did. I went to each of the blocks and the pulley, and I looked at them separately, and I did the good old force diagrams. It's just now with the pulley, we need to think of those forces as what torques do they produce? Because it's the torques that need to balance when we have rotation. If you don't want rotation, all the torques have to end up equaling 0. So all the clockwise torques have to counter the counterclockwise torques. All right, any other questions on this one? All right, hearing and seeing none. Let's go look at the ones from chapter 11. So I have 38, 39, and 85. Okay, so I'm sharing my screen again. Okay, so here's 38. 39 is right below it. So I don't think I'm going to do both of them because they're pretty similar. But Actually, yeah, we'll do both of them because 39 we're actually calculating it, and 38 we're just looking at what directions these things are going. All right, so for 38, we're going to use the right-hand rule to figure out which direction this vector is pointing. Right, so where the angular momentum is pointing. And then we're going to actually calculate the angular momentum of those particles and then the total angle or angular momentum. So let me draw the picture so I can get all this information here. All right, let me put some units on here. I'm just going to mark where these points are because I think that will make it a little bit easier for us. And then I'm also going to write down the masses so we can jump right into question number 39. So M1 is 0.1 kilograms. V1 is 20. M2, 0.2 kilograms. V2 of 3 minus 3. M3, 0.3 kilograms. Velocity at minus 1.5. And then that's for 0.4 kilograms. And its velocity is minus 4. Okay, so I'm going to turn off the screen. All right, so here's our picture. Here's all the mass information, mass and velocity information for later. But let's first talk about which direction the angular momentums are going to be for these guys. All right, so how do we calculate angular momentum? Do you remember which vectors we cross to get it?
Oh, we cross.
Okay, so
Forgot
vector,
about that.
I just call it Victor vector. Good Lord. Okay, so Senior Vector just said that we're going to cross the vectors R and V. Okay, so the way that we define it is angular momentum is R cross V, right? It's actually R crossed with the momentum vector, so R cross P, but P is going to point in the direction of V because momentum is mass times velocity and mass doesn't change the direction. Okay, so here's how we're going to do this with the right-hand rule. So use your right hand. And mostly I'm throwing this out at Max because remember he was, the last time he said he did it with the left
I
hand.
remember from that time.
Yep, okay, so we're going to do R cross V. So I'm going to do it where I'm going to take my palm so that it's lined up with R. And R is always going to be from, let's go with the origin. Basically, you pick a point, but you think about going from R, and then you want to curve your hand. You want to curl it in the direction of V. So let's think about this one that's up here, 0, 2, the one that's up at 0, 2. So here's my R. In this case, R does this. Now think about that V being down here. If I'm going to start at R and curl towards V, it's going to look like this, which means my thumb is going to be pointing into the board. or for you guys is going to be into the paper or into your computer screen, or however you want to think about it. So for that one, it's going to be pointing into the board. All right, so far so good. So let's think about this guy over here, the one that's pointing down. So now R looks like this. So imagine taking this velocity vector and putting it down here so that they're starting at the same location. All right, so this is my R and that's my V. I need to put my palm in the direction of R, and then I need to curl towards V. So for this one, I'm going to line up this way and curl towards V. And so that one's pointing out of the board. So I'm just going to write here, this one was in, and this one was out. So the fact that one of them was pointing in and the other was pointing out totally makes sense, because these velocities are trying to rotate in opposite directions. The first one we did is trying to go in a clockwise direction. The second one is trying to go in a counterclockwise direction. So we should have opposite orientations on those two vectors. All right, so okay for those two?
Yeah.
Yeah. All right, so let's think about the other ones. So let's go to this guy that's down in the fourth quadrant. Okay, so now R is pointing here, and V is pointing in the same direction. So what are we going to get now? So Victor says in. What do you guys think? Is he right?
Yeah, I think so. I don't know,
Because
that
what
one's kind of
in,
confusing.
well, because what in is going to require is a clockwise rotation.
So none.
All right, so Max, you're saying none with a question on that voice. I definitely hear
Yeah.
that question. But let me answer that question with a none. I'll make it a statement. There is going to be
Nice.
no angular momentum. We're doing a cross product, same as torque. And remember, when we do that calculation, we multiply the magnitudes, and then we multiply by the sine of the angle in between them. So what's the angle between R and V?
0.
It's 0. They point in the same direction, and the sine of 0 is 0. So this is actually going to give us none. So it's not pointing out or in. It's actually a vector of length 0, which feels weird. It's just a dot. But that actually contributes no angular momentum. Think about it like torque. And remember when I was talking about opening and closing the door, it mattered not just where you applied the force, but the angle that you had. This would be like trying to open a door by pulling directly on the edge of it away from the pivot. So basically put your hands on the doorknobs and lean back. If you've got one hand on each doorknob, right? So, and I try to lean back, it's not going to rotate because I'm applying that force in exactly the same direction as that radial arm. So it turns out that this one doesn't point in or out because it doesn't exist. Well, it exists, it's the zero vector. So that one doesn't do anything. So what about the one that's out at 4, 0? So now R is pointing to the right. Our velocity vector is pointing to the left. What are we going to get when we cross that?
0.
That's another one that's going to be 0. Because the angle between those two is pi, or 180 degrees. But the sine of that is 0. So that's another one where we get 0. And that's kind of the same idea as this like pulling on the door, as you're trying to close the door by pushing from the very outside. So again, get your hand on those two handles, and now you push, try to lean into the door. It's not going to rotate. So both of those actually do 0. So if we wanted to actually calculate the angular momentums here, what we would do is we would get the momentums of each of the four, and we're going to take the cross product of their radial arms. So let's do that. So I'm going to do this up here. Let's get momentums first. So P1, it's mass times velocity. That's going to be the vector 0.2, 0. So I'm just taking this mass times velocity. Momentum 2 is going to be 0.6, negative 0.6. So that was this one. Number 3, its momentum is 0, minus 0.45. That's this one. No, that's this one. That's for number 3. And then number 4, that's going to be minus 1.6, 0. That's this guy. All right, so let's actually calculate L for each one of these. So these are going to be magnitudes. So number one was this guy. So if we think about the magnitudes and everything and the angles in between them, so R is length 2, because we're 2 units away. The magnitude of the momentum vector is going to be 0.2. It was length 2, but I multiplied by its mass. And then we need to multiply by the sine of the angle in between them. But these things are perpendicular. And so the sine of 90, of course, is 1. So this gives us 0.4. And do you remember what the units on these are?
Rads per second. I don't know.
Okay, so let's think about what momentum is. Momentum, that's going to be kilogram meter per second. And so that's what this thing is. This is kilogram meters per second. But then we're multiplying by another meter. So this is kilogram meter squared per second. they're terribly cumbersome units. But that's the magnitude for L1. But the question is this plus or minus? And let me remind you, we're talking about this guy right here. This is number 1. So Victor says plus. Plus because it's in. Followed quickly by an O. So it is all about whether it's in or out, and in is usually negative. Remember that positive is for counterclockwise rotation. So since this is going clockwise, it's actually a negative. So even though its magnitude is 0.4, because of the fact that it was clockwise, what it actually gives us is negative 0.4. So I'm just going to put a circle around that because that's what we're going to add when we add it to all the rest. Okay, so let's look at L2. So number 2 was this guy. But I'm not going to calculate. How much angular momentum is that going to have?
0.
That one's got 0. We already talked about that. That vector doesn't point in or out, so it does nothing. Okay, so then let's go to L3. 3 is, nope, 3 is this one. So that one we know is going to give us some momentum. So let's get its radial arm. So we need to know how far away it is from the origin. Well, that's why I put this point here. It's at -3, 1. So if we want to know its distance away, that's the Pythagorean theorem. And it's going to be the square root of 10. 3 squared is 9, 1 squared is 1. So that's the length of root 10. The magnitude of its momentum, if we look at over here, is 0.45. And again, the angle in between them is 90 degrees. They are orthogonal, they're perpendicular. So we can just multiply those. Let me get a decimal approximation for that. So 0.45 times the square root of 10 is 1.423. We'll call it 1.4. So again, that's its magnitude, but is it plus or minus?
Plus.
And this one's going to be
Plus,
plus because it's trying
Plus.
to go counterclockwise. It's pointing out of the board. So that is what it is. And then if we go to number 4 is this guy over here. And we saw that its angular momentum is also 0. So then what's the total angular momentum for the system?
1.
It's 1. So we add all these up. And so the sum of the L's is 1. And it's a positive 1, which means that this object is actually going to be rotating in a counterclockwise direction. So in essence, this particle, the one that's moving in clockwise or in a counterclockwise direction, is more than making up for the one that's trying to move it in a clockwise direction. So there's still some left over, so that this entire thing has counterclockwise angular momentum. Whew. So even particles that are moving linearly can still have angular momentum, even if they themselves are not rotating, because angular momentum is really a property of the system, of the entire object, or the entire set of objects. All right, so is that better for 38 and 39?
Yes, thank you.
Yeah.
Okay, cool. You're welcome, Ralph. Okay, so then the last one, I have subsequently lost that number. Hold on. 85. Okay, so 85 from the same section. So let me share the book again and let's go look at it. All right, so 85 says, what is the angular momentum of the moon in its orbit around the Earth? And then it says part B, how does this angular momentum compare with the angular momentum of the moon on its axis? And then they tell us this little fun fact. Remember that the moon keeps one side towards Earth at all times. All right, so let me stop sharing here and let's talk about this.
So first of all, fun fact, let's look at that bit where it said, remember that it's got the same angular momentum about its orbit as its axis, rotation on its axis. So it is kind of a curious thing about the moon. I don't know if you've ever noticed this, but the bit of the moon that we see is always the same. I don't mean the bit that's lit up, right? Like it does go through phases. But if you think about that circular piece that we see when it's fully bright, it's actually the same even when it's fully dark, when it's like a new moon. So think about how that has to work. Let's do it this way. So here's a coffee cup, styrofoam cup. So let's think about this small bit as the face of the moon that you see. Okay, and then my fist is going to be the Earth. This means that as the moon goes around, we're always seeing the same face, right? So that's what's happening as it goes around the Earth. But I want you to think about that cup. What are you seeing happen to that cup? Well, at this moment, the big end is towards you. As we come over here, now the big end is on this side, and then over here, the big end is towards me, right? So if you were just to look at the cup, you see the cup doing this. The big end was towards you, then it went over to the side, then it came towards me, then it went over there. And notice that it's also rotating on its axis as it's going around the moon, or the Earth. It's timed so that it's exactly the same. Well, let me put this into the language of the Earth, because I think this makes more sense if we think about it as the Earth. So let's change, this is the Earth, and this is the sun. So as we go around the sun, by the time we come back, that's 1 year. As we go around in a circle, just rotate on the axis of the Earth, that's 1 day. Now, for the Earth, the same part of the Earth doesn't always point towards the sun, right? We know this because we actually have day and night. There are times when it gets dark here, right? So as the Earth is going around the sun, it's spinning, but much faster as it goes around. But the moon is in perfect sync, so that 1 day on the moon is actually equivalent to 1 year of the moon. But I'm putting year in quotes because it doesn't take a year for the moon to go around us. But if we lived on the moon, one entire trip around the Earth would be the same as one rotation on the axis of the moon. So it'd be like on Earth, a day being equal to a year. So it's kind of weird. I think it's pretty amazing that it's synced up that way, but that's kind of what they're getting at there. But I digress. right? This is not astrophysics. This is physics. But it is a
One
cool
and the
fact.
same.
What's that?
One and the same.
Yep. So we are going to use that fact though when it gets to the second part of the question. So the first part of the question was just, hey, let's figure out what the angular momentum is as the moon orbits the Earth. So what do you need to know in order to calculate angular momentum? And we have multiple
R.
options. Okay, so for sure we need R. So we need to know the distance between the Earth and the moon. Okay, well, we'll get that in a second, but we definitely need to know that R. What else do we need? Okay, so Eduardo gives me mass and velocity. If we have mass and velocity, that will give us our linear momentum. And then we have seen, like with this problem right here, where if we know the linear momentum, we can use that with the R to actually get there. Okay, so yep, we could do that. We can definitely calculate the mass of the moon. Well, not calculate, we can find that number, which still leaves us, we got to figure out V. Could we do it in another way?
Perhaps time, how long it takes for it to orbit.
Okay, we definitely
And then
want to
find a
take
velocity that way.
Yeah, especially if we're going to go with the mass and velocity idea. If we want to find its velocity, we do need to know how long it takes for it to go in an orbit, because then we could actually calculate that. So what do you guys think? I say we go with that. Let's just go with good old mass times velocity to get our linear momentum. And then we can multiply that linear momentum by the radius, knowing that, again, since it's a circular path, the R and our velocity are going to be tangential, so that the sine of theta is going to be 1. So let's do that. So let's go get some information. Now, I have no idea what these numbers are, so we're going to explore this together. Let's just go Google it real quick. So I'll share my screen. And we'll just do a quick Google search for all these quantities. All right, so first things first, let's get mass of the moon. Okay, so it's kind of big. It's 7.35 times 10 to the 22 kilograms. All right, so there's the mass of the moon. What else did we need? We needed distance from Earth to the moon, right? So let's try that. Oh, and I totally just saw it and didn't catch it. All right, so distance to the moon in kilometers. All right, so there's going to be our R. So 384,400 kilometers. And then I think the one other thing that we needed was the amount of time it takes for the moon to go around the Earth. So let's just, how long does it take the Earth, or no, moon, to orbit the Earth? Hey, look at that, 27 days. We'll just use that number. All right, so I think we're good. I think that's all the information we need. So let's see if we can put that together. So I'm going to stop sharing and we'll go to the board.
All right. So let's start by getting the linear momentum. So then we can multiply by the r. So the angular momentum is going to be r times m times v. So in terms of the r, we've got 384400 times 10 to the third, because we need this in meters. We've got our mass in kilograms, so we'll just go ahead and use that, 7.35 times 10 to the 22. But now we need to get velocity. So velocity is a distance over time. So that then, think about the moon going around the Earth. The total distance traveled is going to be the circumference of that circle, which is 2 pi r. So our v is going to be 2 pi times our r. Divided by the total amount of time, which is going to be 27 days. But we need that in seconds. So to convert, 1 day is 24 hours. 24 hours, there's 3,600 seconds per. So we need to multiply that by 86,400. That's our number of seconds per day. So if we calculate that real quick, that's going to give us our speed in meters per second. So maybe you guys can back me up on this, but I get 1,035. And we'll just call that 0.3. So we need to multiply that to this. So the angular momentum then for the moon as it's going around the Earth is an incredibly large number. 2.9 times 10 to the 34. And again, this is kilogram meter square per second. So all I did was I calculated the actual momentum of the moon, the linear momentum, and then I multiplied it by the r to get the angular momentum, which is the same pattern we've seen with just about everything. We just multiply by the r to our linear amount to get our angular amount. So we had to do a little data mining to get this. We had to go find those numbers, but now that we got them, we're good. Okay, so then part B, remember part B said, how does this angular momentum compare with the angular momentum of the moon on its axis? So how are these going to compare?
They're going to be the same.
Yeah, they're totally going to be the same, because that's what makes it so that we always see the same portion of the moon facing us. So it's a different kind of rotation, but it has to be equal so that relative to the Earth, it doesn't appear that there's any rotation. Anyway, fun fact. And this is actually a much faster way to calculate that angular momentum of the moon as it's going on its axis than the other way, because we'd have to calculate a moment of inertia for the sphere and do all that kind of stuff. This is actually just a little bit faster. All right, so how is that for whatever number this was, 85? Is that better? Okay, yeah, you're welcome, Eduardo. Hopefully it makes a little more sense. All right, so cool.
Yeah.
All right.
That's wild.
It is. It's pretty crazy.
And as far as I know, there aren't other objects in the solar system that do that, that have rotations that are the same as their revolutions. So it's pretty unique. It feels like it's coincidence. I don't know. There might be a reason that just through like tidal forces and stuff that cause that to occur. But it is pretty amazing. But there are all kinds of unique things that we see in the solar system, like the fact that if you look at all the planets as they go around the sun, all their orbits are pretty much in the same plane. You know, so like if you're looking from the side, you would see, you know, Earth going in its orbit and Jupiter in its orbit and all that. Well, that's true except for one, and that's Pluto. Pluto's at like a really weird angle, which I know is technically not a planet anymore. But that was probably because it got caught at some point as opposed to being formed by the dust that was in this, you know, nebula as it started to rotate. Because like think about rotation, right? Think about rotation. We've already seen, like when we're talking about merry-go-rounds, that when you're on the outer part, you tend to go out further, right? And I even mentioned how the Earth is kind of squished down. I think I mentioned that to you guys. If not, that's really wise. If you look at, you know, these angular quantities, when you're out at the equator, you're spinning faster than if you get closer to the pole. And so it causes the Earth to bulge. So the Earth is actually, we call it an oblate spheroid or an ellipsoid. You guys are probably not there quite yet in calculus. Have you started talking about? Oh, you got there?
No, we are actually. Yeah.
Okay. So the Earth is actually an ellipsoid, right? So the equatorial radius is longer than the polar radius. Well, so think about that. That's just from the Earth spinning. Well, imagine that we just have like all this dust that came from the eruption of, you know, from like an explosion of a supernova or something like that. So we got all this dust and it starts spinning. Well, it's going to want to bulge, right? And eventually that sort of like, we'll call it polar radius, is going to decrease. And what you end up with is like a disk, like a spinning disk. And that's what happened in the solar system. And then all the material that was in this disk started coming together. When we start talking about gravity, which is coming up in the next chapter, a little preview for you is that, you know, any two masses attract each other, right? You already know this gravitational force idea. Well, so all that stuff that's out in the solar system, in this big disk, starts coming together. Well, in the center, there's a lot that's really close to itself. That forms the sun. And it's so dense that it starts burning itself, and you start getting, you know, burning is not quite the right word, but you get fusion and stuff like that. You get nuclear reactions, and then voila, there's sunlight. Okay, well, other chunks out here do the same thing, and locally they start coalescing, and those form the planets. You know, and so you get the different planets, different kinds of planets, depending upon what stuff was there, what materials were there. That's why we have like the rocky planets like Earth and Mars, and you have like the gaseous planets like Jupiter and Neptune and stuff like that. But anyway, but all those things are kind of in the same disk because of how this has been spinning. So almost all the planets are like that, but then you get things like Pluto, which probably didn't form at that time, but just came wandering by and got close enough that the sun's gravity caught it and basically put it in orbit. We have all kinds of things, like that's how comets end up doing what they're doing. But there are also some other weird things, like you know how, like if you look at the rotation, the spin of the planets, most of those are pretty perpendicular to the plane in which we're traveling. Like Earth's is off by, what's it, 23.5 degrees. That's what gives us our seasons. So in the summer, our part is pointing towards the sun. In the winter, our part is pointing away, right? But most of them are pretty much upright. I believe, don't quote me on this because I'm going off memory. I think it's Uranus is actually tilted sideways so that its axis of rotation is actually in the plane. So instead of spinning around like that as it goes around, it's spinning like this as it goes around. That would be really trippy. Like if you were to think about what days would look like and seasons would look like on Uranus, it would be like insane. But anyway, you get all kinds of weird things. I think this is one of the reasons I like astronomy, is there's so many wild, crazy things going on. I think it might be Uranus as well that has one of its moons orbits the wrong direction. Like it's got a handful of main moons, and most of them are, let's say, going clockwise, but then there's one that goes counterclockwise randomly. That's another one that probably got caught at some point, and just ended up taking an orbit going in the other direction. So
I don't
Anyway.
know if I brought this up. I don't think I did, but I was listening to Star Talk, Neil deGrasse's podcast, and he was saying that evidence is suggesting that Saturn's ring wasn't around millions of years ago. Like, say the dinosaurs were to look at Saturn with a telescope, they might not have seen rings back then.
that's kind of cool. I haven't heard that. But you know, the ring formation, there are a couple of suggestions on that, and one of them, and this would make sense that it's not very old, is from collisions, right? Like you have a couple of bodies that come and collide and basically just, you know, go into powder, for lack of a better word, and then that stuff gets kind of caught into orbit and does the same kind of thing, falls into a plane and gives us the rings. But yeah, the rings of Saturn are really cool. And I don't know if you guys know this, but Jupiter has rings, as does Neptune and Uranus. And so it's probably a good bet that all really large planets, even those that are not in our solar system, will probably have rings as well, just because of their large gravitational fields. So, but
what-
you got to have
Would you
material.
say over time, like Saturn won't have its rings in like a couple million years or something like that.
I'm not sure. He didn't really go into detail about that, but I mean, it's possible if say more material, like bigger material, enters it, it could form another moon in time because it'll coalesce at some point.
Yeah.
And that's definitely what it wants to do. And you also have the moons that sort of help keep the rings where they are. They call them shepherd moons, but it's basically their gravitational attraction kind of balances, and so keeps all that material where it is. I mean, it's pretty amazing, and astrophysics is a really cool subject. I definitely could have seen that being something I went into, but alas, I do this. So, all right, well, hey, let's take a break. I'm going to pause